Hey folks, thanks for tuning in. In this video, we're going to be talking about this Kaggle contest that I have on the screen, Child Mind Institute, Problematic Internet Usage. This contest I found interesting. The problem itself, I think, is interesting in that we are trying to detect kids that have a problem with the internet or are addicted to the internet. From a data science perspective, I also found it really interesting in that we have a lot of messy data. So there's a lot of missing data. There's a lot of features that are given to you that simply don't work out, that you need to kind of sort through and figure out where there's noise. And even the features that are relevant to making predictions are also noisy, and figuring out how to extract the signal from that I found to be something that was an interesting problem. And we're going to be going through the just the first place solution and how he figured that out and how he dealt with it. I thought was a cool thing. So anyway, without further ado, let's just jump right into it. Yeah, like I mentioned, can you predict the problematic internet usage exhibited by children and adolescents? So right, we're just trying to predict kids who have basically an addiction to the internet. The data that we're the thing that we're trying to predict is called the Severity Impairment Index, and this is, from what I gather, it seems to be a designation given by a physician. So 0 doesn't have this impairment, and 3 has a severe impairment. The data that is given to you, two types of data. So it's a train CSV file, which is like reference data, and then they have this actigraphy file, which is given to you in a Parquet format. This is wrist-worn accelerometer data. So the train data is what I would call reference data for each kid. So just demographics, the sex of the participants, internet use, how many hours that they are using per day is reported by them. And other stuff of like their fitness and their BMI, how many pull-ups they can do, things of that nature. One thing to mention about the dependent variables. So you have to predict the SII. Ultimately, between just a categorical value between 0 and 3, but that's derived from this field, which is also given to you. This is a continuous variable. So the folks who were doing this contest would typically use this to train their models, and then after they had done making predictions with their trained models, to do some kind of optimization function to bucket it for categorizing with SII. It's an interesting technique, like kind of after the fact that the model makes predictions, which we'll be getting into as well. The actigraphy stuff. So if you've worked with any Kaggle, any accelerometer data before, this should be familiar to you. If not, for this contest in particular, it's not you don't have to get too much into the details of this. But this is basically, all this stuff is kind of how the thing on your wrist moves around. This was what it's tracking over the period that the kid is wearing it. Oh, and I guess another thing that was surprising to me, and even this the image of what this of what they use for this is showing the kind of a graph of that type of data. And there's another Kaggle contest that was trying to detect when people were falling asleep. So people wearing this wrist-worn monitor throughout the day, and then trying to predict like when they went to bed and when they actually fell asleep. And that was done by taking images of the accelerometer. So building graphs and turning the contest essentially into an image recognition problem. And that was actually what I thought was going to be happening here, but it turned out that because essentially what we're doing is categorizing stuff, we're not trying to find a point in time like that, like the other contest that I just mentioned was, that this data just essentially got squashed and added on to the reference data, the CSV file. We'll show how those techniques worked in a second. But yeah, a lot of surprising things in this contest. A lot of things that I thought were kind of passé in terms of meaning that older models that were not in use by machine learning anymore, that turned out to be part of the winning solution. So that's why I found this contest to be interesting. Okay, getting into this notebook here. This is like I said, it's the first place notebook. I just took a fork of that notebook, essentially so I could add in a few more data frames to just show what the data looks like throughout the processing of it, just simply for making this video. Anyway, but I'll put a link to the original one in the description, not the link to my fork. Okay, so just regular stuff here, right? NumPy, Pandas, OS, scikit-learn stuff, cloning the model as we kind of go through cross validations. All this stuff should be familiar to you. If any of this stuff is not familiar to you, this is probably not the video for you. There's a lot of basic machine learning stuff out there. Sorry if you've watched so far and wasted your time a little bit. Oh yeah, so more interesting stuff. Like I was mentioning, a lot of things got used here that I thought were passé. So PCA is one of them that gets used here. And in other Kaggle contests, I typically see UMAP. So PCA is just principal component analysis. It reduces the feature set. It kind of looks for features that are correlated together and does a bunch of other things. It assumes a linear relationship, and it reduces features from however many features you want to how many features that you tell it. Trying to reduce it to the principal components. UMAP is the one that I find more popular on Kaggle, and doing frequently what people will even do is they'll do UMAP and then they will use something like k-means clustering to even reduce it further. So you just like do UMAP and then you do a group, so you can reduce it to even just one column. So you're really like getting down to the essence of something that you have a little bit of signal in and maybe want to just have groups from. But PCA I just haven't seen used on Kaggle. I can't remember I've ever seen it used in any winning solution. So something kind of surprising there. Oh, the other thing, you actually only use lasso from this line, lasso CV from this line. It uses for imputation. Another model that I thought was completely out of fashion and nobody used anymore, but got used here. Oh, another model that he used, extra trees regressor. So in the final ensemble, right, it's just the kind of the usual suspects of these gradient boosted trees in a big voting ensemble. And he added in this other one called extra trees, which I was absolutely not familiar with, and I had to read a bunch about. So if you're familiar with random forest, which hopefully you are if you're watching this video at this point, extra trees works like random forest, except it's even more random in that it chooses. So random forest will choose random features and a subset of the features and then build a tree that way. Extra trees does the same thing. It chooses a random set of features, and then it randomly selects what feature it's going to split on, and then it randomly selects the split point. And I did not make sense to me how this could be a useful model until I just read a whole bunch about it. But essentially the model is useful for data like this where it's very noisy and you don't want the model overfitting to any point of noise. And the way that it works, the way that it makes good predictions is that the trees are making orthogonal errors to each other. So interesting technique or interesting model to choose that I just it was an old school model that I was not aware of because it just totally fell out of fashion. So cool. Okay, so my little outline over here. So just for notes in this data set, right? So train is going to be we're loading up the CSV file here, just calling it train. That's going to be the leftmost data frame. Train DF train, as we kind of work through this, is going to be the time series stuff that gets added on after that. So just, I guess, keep that in mind. Okay, so moving on. So squashing the Parquet data. This notebook's a little bit out. I would have liked to see this notebook organized a little bit better. The functions are kind of all over the place. It's very well put from a computational standpoint. It's really well put together. I don't want to diss on this guy who won this Kaggle contest because he's clearly really great, but just kind of how like just reading the Jupyter notebook is a little bit messy for my taste. Sorry. Okay. So load time series. So load time series. This is just kind of putting a big loop together to pull out all of these Parquet files. Another cool thing that I learned about Threadpool Executor. Maybe this is more common than I thought it was, but I hadn't seen this before. So I'm very familiar with JobLib, which you can take your CPU or tensor processing unit and tell it to run a bunch of stuff in parallel. So if you are doing like you're looping through a big data frame and you're slicing it up and then you're putting it back together, that's a useful technique. Threadpool is essentially doing that and pulling from an API, so multiple pulls from an API, or in this case, we're doing multiple pulls from a file. From a directory. I'm pulling a bunch of files from a directory. So that's what that's doing there. And then processing the file. So here just doing like a little bit of like just dropping the columns, nothing too big. And then we're doing return time features. And this is where all of the squashing happens. So we're doing basic feature extraction here, percent that the device wasn't worn, sum total of significant movement, tagging for day and night, doing all of this stats for the key and stats for the all these variables. So we're just returning stats, right? So that's kind of all we're doing here. We're just taking. So if you imagine this big Parquet file of how much this person wore this accelerometer during the day, what the accelerometer is doing, and so like each line in this Parquet file is, I think it's 15 seconds or something like that. So this huge file, and we're just going to take stats from all of this, and we're just going to get stats on each of those columns, and we're going to squash it down to one row of data that we're going to add on to the CSV. Right. So, and then after all of that, right, this is the what we're extracting here. So like I said, we just have 75 columns of just stats coming off of this accelerometer. Next step here is to use the standard scaler. So as you can see, like this stuff is kind of all over the place, right? So you have like 1500 and like these tiny little decimal points. So we're using a standard scaler to just squash it down, right? So the standard scaler is just the mean at the end result here, the mean of all of these, all of this stats here is going to be 0 with a standard deviation of 1. So just kind of squashing it down and normal. It's a way of normalizing the data is a better way to say it. Again, this is another technique that I probably would not have thought of if I was doing this contest in earnest. And the reason why is because gradient boosted trees are good typically at dealing with data that's not normalized. And so I'm just, I guess, a little bit surprised that this technique was found to be useful. I mean, maybe it was useful because he wanted to reduce it with PCA and sort of, giving the model all of these all of these columns at once is not going to be useful. And the whole goal here was to reduce it to PCA. It was to reduce it to give it to PCA. So that's probably, I think, what the thinking was here. Yeah, it's cool. All right, so next steps here. So, so we're just doing simple mean imputation. Any nans here in that file in this above here, we're just going to fill in with means, and then reducing it to PCA. So where is this function? So taking in the data frame, and then simply reducing it via PCA, and that outputs something that looks like this, right? So we reduced it from these 75 columns with all this, this giant variety of ranges of different columns down to 15 columns where we're all basically centered around a mean of 0 and the PCA. So PCA, again, PCA assumes a linear relationship between data points, and it's going to look for data that's correlated and eliminated and try to give you back something that a model can use to predict on. Okay. Cool. All right. So yeah, next step here is all right. Yeah, just merge it. Sorry, I probably didn't need another bullet there for this one. So clean features. So this is just doing good old-fashioned feature engineering, where he just simply looks at each of these columns and determines what values are implausible and just fills it in with a NaN. So, for example, this first one here, just the body fat percentage, is implausible, especially for kids, to be less than 5% or to be greater than 60%. So probably those readings are bad, and we're just going to fill them in with NaN. So the same thing with, all these other, metabolic rate and fat-free mass index. I didn't look up these the proper ranges for these. I'm just assuming that what he did here is correct, but just good old fashioned, just like going through each column and making sure that you have, and just cleaning your data. It just goes miles and miles here. Just basic stuff of like data cleaning is really nice to see. Okay, so doing that. Oh, right. So then he's finally doing this feature engineering function. Where is that? It's way up top, right? Yeah. So this function is doing more of the. So after cleaning the data, after cleaning the data, what he's doing here is he's essentially bucketing a lot of stuff together. So for example, the age column. So big differences, right? I'm sure you remember. I'm sure folks here know kids, right? Big difference between 5, 6, 7, 8. As you 8 and 10, less of a difference, and on like that. So as you can see, it's kind of just using enumerate, and we're just anything younger than 5 is going to be group 0. Between 5 and 6 is group 1, et cetera, et cetera. So we're just basically telling the model where to, like, what is important, right? So that how to bin stuff. And same thing here with BMI did binning here. Anything lower than 16.3 or higher than 16.3. Actually, I'm not sure what you did here. Anyway, but binning, taking all the stuff, actually going through these columns, determining where to bin them and what made sense. I don't know how he came to these numbers, but it's cool that just looking at how this was engineered, and made for a good feature. Right. So did feature engineering, and then what else? Oh, and then more. Then here we're just binning some more data. And these were not hand coded by each column, so we're just simply taking all of these columns and just doing 10 bins each. If you look at this function, we're just simply dividing it equally by 10, or yeah, by 10. So just figuring out which bins are there, though using a couple other methods from Pandas that I was actually unaware of until going through this. So qcut and cut, that figures out the edges of the bins based on whatever number that you put in, and actually cuts them up. And then we get this. So this data frame is now looking like this. We still have a bunch of nans in there, right? Because we've taken out a lot of values that don't make sense, and that's what the data frame is looking like at this point. Oh, more noisy stuff in this data. Just a bunch of columns that were just simply not in the test set, so we just had to simply get rid of them and not use them. I guess they might have worked for imputation, but so that's why we're doing them later. Okay. All right. Oh, yeah. So now we're looking at some of the. So this is the continuous variable distribution of score. So looks. If you're familiar with the Poisson distribution or Tweety, right? Big bunch of zeros and something that looks kind of normal-ish after that. And as you see later, when we optimize the gradient boosted trees, a lot of them found that Tweety and Poisson were the optimal distributions for their hyperparameters. Okay, so now this is imputing all of the nans in here. So what this class basically does is we're looking for features that have enough data in the column to actually make an imputation on. If they don't have enough data, then simply using the mean of the column. If they do have enough data, then we are imputing with this is just looking this is just building a data frame to figure out what the cutoffs are. Oops, sorry, down here. So if it doesn't have it, then we're imputing with Lasso CV. So like I mentioned, this is if you'd taken a machine learning course like 10 years ago, maybe even 5 years ago, talk probably a lot about Lasso. That's not true. Lasso is still used for a lot of regularization functions, but using it as a model that you would use to predict is, I think, uncommon. I think even using it for imputation, like using here, is uncommon. I would have most likely used k nearest neighbor or a tree, or just simply using the mean. Using Lasso is an interesting way of approaching it, which worked. So yeah. Oh, Lasso CV is the difference between Lasso CV and regular Lasso is it simply knows the you don't tell it the regularization number. It just figures it out for itself. Okay. And then all right. So now everything is imputed. Everything is all the nans are filled in, and now what he does is again, this is a little bit out of order. These functions don't get called until way later. Same thing with the so now what he does is he does this giant Optuna parameterization function. So a lot of this stuff gets used later for his cross-validation, but effectively, so what he does here is, where is he calling this? All right, so yeah, calling the optimization stuff. So run optimization. So this is, I didn't run this myself, so I'm assuming that this took him a good 10 hours or so to run. On the Kaggle hardware, it probably would be something like that. It's just because he's running the cross validation to find parameters with I think 10 seeds that he puts in to try to suss out the variance, which is interesting because everything else is kind of binned and geared towards dealing with very noisy data, and the hyperparameters that he winds up landing on and using a huge amount of compute for are really, really extremely precise. I think probably over precise, and maybe we'd call it false precision. Anyway, how this works is we're using Optuna. Optuna is a library that is geared towards machine learning hyperparameter tuning, where you give it a bunch of different parameters and it does this grid search to find the best parameters for your model. So you start it with so just giving it the XGBoost parameters and the LightGBM parameters. You give it you tell it what to kind of look for, the learning rate probably between 0.01 and 0.05. For the XGBoost and LightGBM have slightly different parameters, but they're pretty similar. CatBoost, same thing. And then Optuna is going to go and do a big grid search over everything. He's doing this he did this with cross validation, meaning that we're just taking we're going to take a bunch of different folds from each model for the data set, folds of the data set for each model, and do it a bunch of times and take an average of the parameters that it was that Optuna found. So he broke it up here actually instead of doing a bunch of seeds for this cross validation for the Optuna version of this, so he could break it up, and later when he has the parameters to just have this cross validation by itself. Okay, so that being said, if you've done any cross validations of models before, this should be pretty familiar to you. Everything here is just simply taking folds and just training your model over and over again to average whatever it is that you're looking for. In this case, we're looking for parameters. Later we'll be looking for the actual prediction. One thing that I want to call out is that he actually gives it explicit weights. This is not a technique that I have actually used before, and I really like it. So typically how I would have, we have an unbalanced problem here, right? A lot of zeros and very few threes that we're trying to predict. So typically how I would have done this before would be stratified k-fold. So that, you want to make sure that for each fold that you're training on, that you have a higher you have a consistent number from each category. What he does, though, is what this weights does is actually, let's go and look at this function. So what this calculate weights function does is it I actually wrote a little bit about it. So it creates bins to pass the models based on frequency, right? So, and then it does a straight inversion to give the categories that have the fewest, the least amount of frequency, the most weight. So if you just imagine each row has a weight, and each weight is going to be based on the category that this that the y variable falls in, and we're going to weight those more heavily, and then you pass that to the model, and then the model, the gradient boosted tree will focus on whatever you're telling it to focus on. It's a good way of dealing with multi-categorization in an unbalanced set. It's a very, very good technique that I'm really glad that I learned from this. Okay, moving along. Okay, so right, so after doing all of this, runs runs Optuna, runs that whole cross validation for finding parameters, which I can't imagine how many hours it took. Hopefully, he was sleeping while this was running, and then we get this. So, like I mentioned, very very precise things that were very very precise hyperparameters that we're coming out with here, and probably false precision. Probably isn't going to matter too much, but okay, it's fine. Oh, yeah, and extra trees. Like I said, I had not worked with this model before. Interesting to see that. I don't think actually. I don't think he ran Optuna on this, but anyway, interesting to see. Like it just doesn't have much, right? It does nothing, not too much that you're telling it to do. Okay. Right. So then training and predict, right? So, right, calculate weights. We just went through what this does. So this is the same function that was used in the optimization. So we're when we're doing this for real, right? You want to do this on train as well. Sorry, sorry. We're doing this over the whole. Sorry, when we're doing this for real, we're going to use all of train, right, as opposed to using uh, the folds in the cross validation. And then here he does, as we're going through this, he does cross validate, and then he does actual fit and train on the whole thing, and he just does that with each one of those. Computationally, right? This is fine, by the way. But just like for this Jupyter notebook, it seems a little messy to me. Like I would, you did all this cross validate stuff so that we can do all of these nice graphs below, and then like fitting the model seems like it should have been done later, but whatever. I'm just probably nitpicking here, and it's fine. Anyway, so from the cross validation, he made some nice plots. I'm not going to get into this code of how these plots were made. Feel free to dig into his Plotly stuff, because I actually think that the charts he makes here are really nice. But you can see like the differences between the models, and they're all pretty the same, right? Like also you can see how noisy this data is and how hard this stuff is to predict. Like you have like it's not like this. If these were perfect predictions, right, it would be like this diagonal line of like dots, right, between the true score and the prediction score. So it's not. You can it's sort of looks all right. You can kind of see that it's not totally all over the place, but it's not great, right? This data is still very noisy. Doing these techniques that we've gone through are doing the best you can with noisy data, but the data is still noisy, so you still are going to wind up with this jumble of mess of looking scores. The correlation between models is also an interesting thing to look at. I didn't really see too much here between differences between the models. I was actually surprised that extra trees I thought was going to be way different than all these other things, but it's just correlated slightly less, I think, with the group instead of like dramatically less. Like I guess maybe that is a big difference, right? 0.96 correlation when you're seeing 99 and 90.99 and 0.98 correlation with all the other ones. So I guess you see a couple of 0.96s in there, but yeah, so interesting. Right. Feature importance. You can go through these graphs. It's just basic feature importance of what the what the various models thought was the most important things to split on. All right, confusion matrix. This is like kind of an overall confusion matrix of the predictions that we made in the cross validation. Nothing too much to nothing. I didn't really get any big insights from this. Zeros are easier to predict just simply because that's probably that's just because it's the biggest distribution. Oh, did I go through the where was the I think we're good. Oh, right. This is what I was looking for. The round with thresholds. So this is So we're taking the continuous variable and we're mapping it to the SII, mapping it to the categorical variable. So this is a optimizer here to fit. Where's calculate? Right. This is so right. We're running an optimizer here essentially to on the cross validation, the training data set to determine where the threshold should be in the most optimal way. So it's right. We're using the evaluation metric, right? So it's important to kind of work that in to lower the score there for whatever we're looking for, and we're doing it. Where was the function here? Threshold. Oh, right. So we're just doing a simple minimize to figure out the. We're just doing a simple minimize to figure out the most optimal places to weight that at. And then after all that, just simply putting it into the final score to make a Kaggle submission. And I guess that is that. Thanks so much for tuning in. I hope this was interesting and informative. And thanks so much for watching. Cheers.